Okay, so hi everyone. Last time there was a problem with the video recording. I don't know if you know, because those who are here don't know that. So I'm not sure what I want to do with this. I mean, I'm not going to record 3 hours again, but I'll just repeat a little bit from the end of the last lecture because that's what I need. In any case, you'll have that. And also at the end of the lecture today, I want to talk about the presentations. One will be tired. I don't want to spend the time where our cognition is highest, right? So last time we started to talk about PRGs or de-randomization, but PRGs for read-once branching programs. We actually started to talk about combinatorial rectangles, but this is for me more or less a two example for that, to that end. And remember, so what's a read-once branching program? It's this computational model. You have a graph. That's where I'm repeating myself a little bit now. W vertices in each layer. You have n or n plus 1 layers, depending whether or not you define a layer like that or like in between. So in between, you should have n. And there is a designated start state and an accept state. You can assume it's one state. No, make sure it's only one. And this model, it gives you induces a function in the natural way, right? So depending what natural is for you, but in the natural way, you read the things, and starting from here, if you end at the accept, you accept, otherwise you reject. So it's a 0-1 function. Okay? And what I said, and I'm not going to repeat that, is that if we have a PRG for with W, which is poly-n, W in general, you should think of it as a parameter, but in this particular case, if you have a PRG for width which is polynomial in the length, and where the error is just some constant, I don't care what constant, and seed, which is, whatever you want, S of n, then you get that BPL is in S of L, I think. Like, if S is like, we've seen come on, this is easy. We've seen S of log n, then you get like, if it's like order of log n, you get DPL is in L. If it's like log n squared, then you get DPL in L squared and so forth. Okay, and we saw a PRG for width 2 using Fourier analysis a little bit. We did that, right? With seed length, which is essentially optimal. We just use an epsilon by a set and prove that the L1 norm of any such function is bounded by n. And I think I told you that there exists a PRG with seed length. That's the log-log rule, which is log of everything. And there's Nisan's PRG, which we'll talk about today. Right. So this is non-explicit, which means that you can't use it for de-randomization because you don't have the PRG to run. You can go over all PRGs, but that will take more space than whatever you want to do. And Nisan's PRG does like log n times that. Good. And I think I talked a bit more. And then we ended the lecture, like we didn't end we started the last part of the lecture by talking about combinatorial rectangles. And these are functions. So it's a function on n inputs, but it's actually a product of n functions on the individual inputs. So every fi is from some m, that's the kind of the size to 0, 1. So this is a function from m to the n to 0, 1. It's essentially the end of these functions. And we call it combinatorial rectangles because the preimage of those, the product being 1 means that you're in the product set theoretic product of the preimages of the FIs of 1s. Okay? And then so that's the recap. It's a longer recap than usual. Then we constructed we constructed a function which I'll now show it's a PRG, but let me say that we constructed a PRG for these functions. And actually, for every length, so we assume n is a power of 2. So for any possible length, 2 to the j, the construction went as follows. So m is the parameter of these functions. So we outputted 2 to the j stuff. And do you remember how it went? Like, what's the difference? Right. So it's recursive.
Without the j.
Exactly. So first you ignore this completely. And then you hash x using that and apply the same function. There are several ways you can do it. If that doesn't seem the most natural one, it's fine. It just means that your brain is calibrated to the other ones. So that's one way of doing that. There are many ways of doing that. But that's a nice way. And right, so it works like this. So initially you output x, and then h1 of x. So for example, for j equals 1, that's what happens. For j equals 2, you do exactly that. But then you do the same thing, replacing every time you see an x, you replace it with h2 of x, by definition. And so forth. Okay. And to start analyzing that, we where is the eraser? It's hidden behind. We talked about the hash mixing lemma. This is more or less where we stopped. So the hash mixing lemma, which is the analog to the expander mixing lemma, which is also a bit analog to the small bias set mixing lemma. It has no name, but that's how I would call it, that you saw in the recitations by Tai. So it says that regardless of anything written there, I'll slow down in a second. I'm just doing it quickly so that we'll all be on the same page. So, for any two sets, okay, maybe I should say even before the two sets. So we're looking at a family of hash functions from M to M, and these are pairwise suffices. Okay, and so the hash mixing lemma says that if you have two sets living in the set 1 to M, then if you want to approximate their density, then you can use if you sample a hash function and use that, which is kind of a degree 1 graph here, which may or may not be matching, then counting the number of edges that goes through between A and B is a good approximation for the actual density of the product. So it's written like in a weird fashion, where you have a probability inside a probability. But I'll say something in a second. Okay, so that's what we proved. We proved that if you sample the hash function as random, then except with a small probability, which you kind of should ignore, a good thing happens. And what's the good thing? So if you consider the kind of the edge that connects x here and h of x there, then that edge will fall in the product, AB, with probability, like if you go over all x's or equivalently over all edges, with a probability which is very close, at most so an epsilon, it's the same thing as the density of AB. Okay. There is this trade-off here, of course. And sometimes we call this the accuracy parameter because it determines the accuracy, and this is the confidence. Right? How confident are we that we have a good accuracy? And typically these are denoted by deltas. Whenever you see an epsilon or delta, you should know that if someone used the right notations, this is the, you are up to plus minus epsilon, you're good, and this is the probability for that to happen, or not to happen. Okay. And I think we stopped there, and then I gave you a theorem. I just said this is what we are going to prove, and I will do that now because I'm going to prove it. But now I'm slowing it down. So any questions so far? Do you want that pace? Actually, maybe that's a good pace to continue the entire lecture. Okay. So any questions? I mean, it's okay if you don't remember something what to ask.
Just a right? It's H1 composed H2, right? So it's H1.
Right. Yes. 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 So there is the notation of not writing parentheses, and I used both of them. Like yes. Yeah. There is no like other way because I like omitting notations as I go. So it's a sign of we understanding each other. It's like a married couple that don't have to speak. Okay, so here's the theorem that we prove. Now this is a very important theorem, not because it's important. It's not really that critical to construct PRGs for combinatorial rectangles. It's important because this is like the frame, blueprint of how you prove things in this field. Yes.
What is the combinatorial?
Yeah, it was somewhere here. It was a function. So you can think of it as two ways. So f is a function from mn to 0, 1. Right, so I think of it as like n-dimensional cube, but the length of the cube is m. So 0, 1 to the n is the hypercube and so forth, but I care about m, which is large today. You'll see why. Where these are any functions that you'd like from m to 0, 1. Okay, but the best way to think about it is, since these are 0, 1, it's really an indicator to, xi being good for all FIs, right? Xi is in the preimage of one of the FIs. So really, you should think of it as no. So I think of x like this, x as good for f, like it's 1. If yeah, you're right. If xi is good for every FI, good. So so you are in. I don't know how to. You are in this set. I'm inventing notation as we go. So x is in this set exactly when the function is 1. No, this is a function. I'm saying that, but I also want to say that you're right that I'm going to plug random things here. But this is a function. For any input, it has either 0 or 1. Right. So exactly. So I want to approximate the expectation of f, in that sense, de-randomize it, by using not all m to the n strings. Good. We're going to use, okay, 2 to the log n times log m strings.
Prove this is random generators for the 2 width 2.
Right. So these are computable by width 2 large RET branching programs, RETM, because and I'm not going to do the general width 2 branching program PRG. We did it for Boolean. For larger RET, it's actually more difficult because Fourier is of the game. You don't have it. It's not hard, but it's harder than this, and it kind of goes in a different direction, which I don't really. So right. So what I'm saying is that, and then we can see if it makes sense. There exists a PRG for, sometimes they call it NM combinatorial rectangles, just so that we'll remember the N and M. With seed length, maybe an epsilon PRG or any epsilon. So the seed length is going to be log n times Okay, log m n over epsilon. That's like, yeah, that it's this PRG really, and that's kind of Nisan. So when I say there exists, maybe I should just say this is the PRG. But if you think about what is a PRG before proving the theorem, then a PRG really is a map from the seeds to the output. So you can think only on the outputs, only on the kind of the image of the PRG, and that in this case is going to be just a subset of that, of size which is 2 to the seed, because for every seed, yeah, it's like from 0, 1 to the seed, number of seeds, to the seed length. So a PRG is really just a few, hopefully very few, points here, such that for every combinatorial rectangle, the number of points that lie in the rectangle is roughly the density of the rectangle. Right, so it's a density approximator. Yes. So you see, usually when you say de-randomize a function, so I kind of ignore that, but I want to. So you mean that there is an input and there is randomness, and here there is only the randomness because there is no input. So in that sense, if I want to de-randomize those, like maybe f has some hidden input and that's the randomness, then you want as best as possible, and that will be this. Epsilon should be constant. I mean, that's the best you can hope for. Epsilon will be constant. Maybe I don't understand the question.
What do we feel like?
Epsilon? Yeah. Usually constant. Usually. Like, depending on what you're trying to separate. Like a BPL version, things is like epsilon. The promise is there is a gap of like 1/3 between the accept and reject, so that's enough. Sometimes it's not enough. You can always amplify, almost always amplify. Yes.
In order, I mean, I think I understand what you're doing, but you need to also claim something about the efficiency.
Right. Good, you're right. This is a PRG for either I should write there is an explicit one, and then we can talk about in what sense is explicit space or otherwise. But when I actually give it to you, it's easier to kind of do it in different, like a more modular way. So this is a PRG, that's the seed length, and then you can look at it and say, well, I can work with hash functions efficiently, both space and time. So you can show, and we will talk about it when we need that this is highly space efficient and also time efficient. But really what I want to say is that this is a PRG. So when j is like log n, so that 2 to the j is n, this is the PRG for this. Okay. So let's start with the proof. So again, I'm trying to show that this is a PRG for combinatorial rectangles. So you're going to give me a combinatorial rectangle, and actually it will be nicer to work in this kind of notation. So instead of functions, we're just going to call this A1 and this AN. These are the sets. And I just want to fall within the product of the sets with the probability which is close to the density of the product. So given A1, given some combinatorial rectangle, which I also like to call L left times A right because of the recursive nature of the construction. So this is the first n over 2 sets, and these are the last. So given that, what I want to show, right, let's spell it out. I want to show that the probability. So in a general PRG, what I would have liked to show is the probability over all the randomness. Right, you use many h's there, so I'm going to call it the h vector. You have j of those here. This is h1 up to hj, where j is log n. So the probability that the PRG, our PRG, falls into the set is roughly the density of the set. That's what you usually want to show. I mean, that's the definition of a PRG. Right? PRG is, this falls there exactly when f on that is 1. And that's the probability of F2B1 under uniform distribution inputs. So that's by definition, that's what I need to show. Right? Is it clear? X is in M. And M is the dimension of the, these sets lives in M, in 1 to M. Right, good, yes. So that's generally the definition of a PRG. We will prove more, exactly. We will prove that not only, when we average over X and H, we get a good approximation, but actually H is kind of worries about the confidence and X worries about the accuracy. So instead of proving that, we're not going to, what we're going to prove will imply that. And we need this, I really want this distinction today. And in general, it's good to have it. So what we will actually prove is that with high probability over the sampling, over the choice of H, only with respect to the randomness coming from X, it's a good PRG. So let's write it. Yeah. So the probability over X that PRG J. Now X is alive and H is fixed when I'm here in this scope. The probability of that to fall in A is close to mu of A. So there is some. I want to show. Let me do the. I want to show that. It's harder than it looks like. Right. So I want to show something like that. I want to find good epsilon and delta depending on J. These are, I know what these are, but I want to kind of keep it like that for a second. Sometimes when I do it, I don't know what these are. I'm just hiding it. But now I do know. So with high probability, except with this probability, except that's a confidence we have. We know that when H is sampled, we know that but for probability delta J, everything is going to be good. And what's good? Well, if you only use X as the randomness to this PRG, so H is fixed, like wired into this function, all of the vectors of H. This is a vector always. Then only with respect to that X, when you average over X, the probability will fall into A is roughly the density of A. So if these are epsilon delta, if you know that, then how can you deduce? I mean, you can deduce that, but without epsilon, for example. Right, it's less than 1, exactly. Also, so it's almost the sum of the epsilon deltas, right? So with probability delta, you don't know what happens, but it's almost 1, the difference. Right, and you can do convex, yes. But like the easiest thing to say is that it's at most epsilon J plus delta J. You can always add the confidence and the accuracy because with probability 1 minus delta J, and that's what you're going. I kind of neglected that. Probability 1 minus delta J is at most epsilon J, and probability delta J is at most 1. I mean, there is only, you can only screw up so much, right? It's almost 1, difference of 1. But, I don't mind, so I'm just writing it like that. I mean, if you did a good job, that's small anyhow. So it's this thing. So you can always, like, if you have this more refined analysis of confidence and accuracy, you can always kind of ignore the confidence and put it in the accuracy if you want.
So this is still a probabilistic, like there exists a set of pages.
Okay, that's interesting. So the explicitness is on the PRG, and now for every A, there will be a different set of H's that works. Right, so it's not like, it's even worse in that sense. In the probabilistic method, usually what you prove is that there is some randomness under some distribution. You work over some distribution. You can prove that there is one thing that works for all. Here it's worse than that in that sense. So this is explicit, and that's the important part. But other than that, for every A, most H's will succeed, but the identity of those H's depends on A, and it does depend on A, because for any H that you want to succeed, I can probably cook up an A that will fail for that.
Like when you draw it,
yeah.
do you have signatures saying with the function that tell you yes, it's
That's yes, and we'll use that. So there is a way to check if an H is good. Efficient, yeah, right, exactly. Right. So what's the seed? Yeah, right, good. So the seed, well, you have like JHs. You have JHs. So let me write it like that for a second. Right, that's the size of the, and then you have like one M. One element from 1 to M. So this is for X. And this is for, H1 up to Hj. J at the end of the day is going to be log n. Now, a pairwise independent family from M to M requires log n bits. It's like this is M squared or something. So all in all, this is like log m, maybe 2 log m, but it doesn't really matter. And J at the end of the day is like log n. So you get, right, at the largest J is log n. So you get log n times log m plus log m, which is redundant here. And it's not what I wrote. Right, good. I wrote something worse. I don't know where it is. Yeah, here. I wrote log n times log n, good, but I then added log square of n, like log of n times that. And there is a reason for that. So what's going to happen, that was exactly the next thing. What's going to happen is that I will have to work with m, which is possibly larger than the m that I'm supposed to work with. So you see, when I want to full combinatorial rectangles, if I increase m and do the job, like you're happy because pulling higher m combinatorial rectangles, you can simulate lower m's using higher m's. Just ignore some of the entries or duplicates or whatever to keep the density. So I'm going to artificially increase m in the proof, potentially. If it's not large enough, I'm going to increase it, and I'm going to full a larger class, but I'm going to have to do it. And I'm going to full a larger class. In particular, I'm going to get a PRG for this. So I'm going to assume throughout you will see where I need it. I'm not going to need it right now, only at the end. So you'll see. But I will need m to be at least like poly, I don't know, something like that. So I'm going to assume this is the case, and therefore this translates to what I said. And if it's not the case, then I'm going to tell you, sorry, you asked me to full m equals 2, but I'm going to full slightly larger things. That answers your demands, and you plug m. M is going to be at least m, the original m also, right? So this m is going to be both m and this. So the maximum or the sum, it's what's right there. It's really a max, but it doesn't matter asymptotically. Yeah. But let's do it. Let's prove that the PRG works, or in particular, the way it's written, maybe epsilon and delta are 1. There's nothing to prove. So let's understand how epsilon and delta evolves.
Let's begin about the H's.
Of course.
So just to understand what we're doing, we're proving that there exists a good set of H's
Yes.
that will work eventually for every A.
We start with an A, actually. Yes, so we start with an A, and during the proof you will see that for most H's, depending on A, for most H's, this works. But you don't want to find an H or something like that. For one application you would actually, but a smart application. Yeah. I see. You thought that there is another stage where you need to find the H also. Actually, I want to say you don't need to, and you don't, but that's a good thing to do, and we will do it. But afterward, so that's an application. So to that end of just proving that this is a PRG, this is already an overkill. We are doing high confidence, like small PRGs instead of one big PRGs, which is written here. Okay, and just to not to the suspense, this is going to be something like 2 to the j epsilon, and this is going to be like 2 to the j over epsilon square m. Right, epsilon without the 2 to the j is exactly the expander mixing lemma. I just wrote the parameters epsilon for any epsilon that you want. This is epsilon. It's not the epsilon at the end. maybe I should say, let's call it epsilon prime. A hash mix, what I say, expander? Yeah, right. So the hash mixing lemma, just you can choose any epsilon prime to get that trade-off. And what I'm claiming is that both of these quantities blow up exponentially with J, which we can work with, but that's what I'm going to prove. Right, the base case is actually obvious. I mean, it's not obvious, it's exactly the hash mixing lemma. Because, yeah. But let's just do it. Right, so I want to analyze the difference between these two, right? And the PRG is defined recursively, but okay, slowly. So, you know, PRG, maybe let's do the probability also. So I'm kind of forgetting about H for a second and looking inside. So the probability over X, that what I want to show is that, I mean, I'm forgetting about H, but I'm writing it, of course. The probability that is in A is roughly mu of A. And that's what I want to show. I want to compare these two. And so I want to. So, and I need to use the induction, like recursive nature of this thing. So let's open this up for a second. So saying this, so ignore that, that's just what I want. But this thing is equal to the probability over X, that, and I'm just going to write this PRG by definition. So on the left, it uses the recursively obtained PRG with X, and maybe let me be more explicit here. You know, let's write it like that, Hj minus 1 vector, right? Let's put the vector J here. And then you concatenate it with the same PRG, really, but when you apply Hj to X, and then use again the same J minus 1 Hs before. So that's exactly that. I just rewrote it. Yes. Another one. Ah, this one, yeah. Yes. But instead of writing it like that, let's just say, I mean, what it is. I mean that this is in AL and this is in AR. Right, the way I wrote AL and AR. So the probability of PRG J minus 1, XA J minus 1 is in A left, and is a very, and has correlation. It's not a product, right? N is bad. You want products. That's what you want. But there is an end here. And the hash mixing lemma allows us to replace this and to products. But let's do it slowly. Okay. Now it looks a bit like a hash mixing lemma. There are two sets, but it's not like you have x's in one set and h of x is in the other, right? You have x sitting here, and you have a function applied to that. And it's a function. I mean, this is fixed. Hj minus 1 is fixed. So it's some function. You can call it f. Let's call it f of x. I mean, I really want to see x, not f of x. Exactly. And this is like g of h, j of x. Right, so what's written here is the probability that f of x is in AL. It's the same f, really, yeah. It doesn't matter, but yeah, it's the same f. Right. Yeah, and you can write, right, but I want to keep this. And f of h of j is in AL. And the pattern mixing lemma, if there was no f here, it was immediately implied that this is close to the product. But, you know, what you can do, as you well said, is you can just, you know, that's actually easier. I mean, in the worst case is the f is 1-to-1. Because you can always take ask, you know, I mean, f of x is in AL, if and only if x is in the pre-image, regardless of 1-to-1 for AL. So you can just replace those sets with, replace this expression with that expression, which is more familiar when you talk about hash mixing lemma. Show it's, you know, deduce that it's close to the product and then go back. Apply f again. So what I'm really saying is that this is up to an additive epsilon squared epsilon prime, sorry, this is the same. So this means that the difference between these two is post epsilon prime, an absolute value. It means that you have PRGJ minus 1, XAJ minus 1 in AL, and when there's the times, this is important. This will also need to probability that the PRG J minus 1 AJ of X AJ minus 1 is in AR. That's like the, yeah, right. That's the density of the inverse pre-images. So what I'm saying is the hash-mix cinema works with functions as well, it just doesn't matter. The difference here is like the difference is literally epsilon prime, but the difference is that now it is as if there are no correlations between the two parts. Am I wrong? Yes. Yeah,
Should there be like on the right, should it be HJ or just probably X?
you're right. Yes. I mean, you're definitely right. Yeah. And sorry, I should write X. If I mean, it's you can call it X prime just to make sure it's not the same as that, but it's in different scope, so it's X. X is uniform. Yeah, no, it shouldn't have been HJ. Exactly. So now it's like two independent samples. That's the point. You want to make dependent samples look independent. Right? If you manage to do that, then you kind of mimic the uniform distribution, the independence, at least for two elements here, using less random bits. Technically, by the way, sampling from H is more random bits than two distinct. It's also M squared, but never mind that. Don't listen to what I just said. To just confuse everyone. So good. So how do we proceed now? I mean, right. So I mean, we still work with like. This is not ideal. That's not the density of AL. Exactly. But by induction, except for probability delta J minus 1, this is up to epsilon J minus 1, the density of mu L. Right? So except to that's I like that. No one likes that other than that. But instead of writing with probability 1 minus, you write except for probability delta J minus 1. You don't care about the 1, right? Delta J minus 1, we know that this thing, let's call it, so that let's call it star left. This is star right. So star left is, up to epsilon J minus 1, it's mu of A left. Except probability over the HSM. Right? So usually this is fine. And same for that. Usually that's fine. It's another usually, so you need to take an advantage. There are two deltas that you're losing. And same for, right. So except with probability 2 delta J minus 1, both of these are close. The epsilon J minus 1 far from what they should be. And so their product is also close. So you get that we are off by, so maybe I should, so except the probability, what I'm seeing is mu A left plus minus, this means that I'm in this range, right? Times mu of A right plus minus epsilon J minus 1. So what's written there is this thing. Forget about the epsilon prime. Only this expression, when we are in a good scenario where we are not in the bad H's, when this is what it should be, plus minus epsilon J minus 1. Same for that, which gives you mu of A, right? This is good. Plus, now there are some errors, which you probably encountered in the homework also. When you multiply things, error evolve. So you get, the error is not epsilon J minus 1. There are two components of epsilon J minus 1, this and that. There's also this epsilon J minus 1 squared, which is smaller and no one cares about. And these are at most 1, so I can definitely say 3 epsilon J minus 1. And I'm being courteous. Right? This is formally. Yeah, no, it's just lazy, but not informal. Right. No, I'm adding it now. I'm just showing this thing.
So I have a question.
Yes. It's really formal. It's just lazy.
It's okay. It shows the way to formalize.
Yeah. I mean, from here, a computer, you have no AI can do it. Yes.
And about the FX,
Yeah.
yeah, doesn't it need to be like the probability of being F1?
No, because I did it. So I'm just saying that you can replace this n to a product using the hash. So with the same, like a product, as is, using the hash mixing lemma, even though the hash mixing lemma doesn't have an f applied to things, and the proof goes by, you first do this, then it's a product of those things, and then you apply f back in each of the individual. Okay, so all in all, you see that epsilon j, what can we say about epsilon j? Now, including epsilon prime also. So we got one error from here. This is the error obtained because we even, I mean, these are like rotten things. They have errors in them. But we didn't even took their product. We took using the hash product thing. So we got this epsilon prime. And on top of that, we got this, right? Even how do we work how do we multiply them correctly? I mean, we still have errors in each of them, and it blows up like that. So all in all, you see that epsilon j, yes, right, and it will. So I'm keeping it epsilon prime, and the delta will depend on epsilon prime also, like in here. Right. So epsilon prime is a parameter for a moment, and I'm going to get rid of it. It's just for the analysis. It doesn't appear like in the construction. Just for the analysis that you choose where to do the trade-off. And so anyhow, it comes up to like 3j, right? Just add them up. So maybe not 2j, but 3j. What about the deltas? Where did we lose? Exactly, we have these two. They are really coming from, you can actually also separate it to like the confidence on which h's. These are coming from the h1 up to hj minus 1. And then there is another one because of aj, because we use the expanded mixing lemma. But I'm not kind of thinking of them separately. So there is the other one, right? Here you have like so the thing from the expanded mixing lemma. So 1 over epsilon prime m squared, I think, m. Right. So that turns out to be at most like 2j times that. 2 to the j times that. Good. This one? Let's return to that afterwards. Yes, I was with myself. I wondered whether I want to do it or not. Probably should have, but let's do it like not offline, but after the. Oh, well, okay. We know the PRG right now. So, right. So let's just finish this up. So we're kind of done really. At the end of the day, this is like less than n squared for j which is log n at the end. For j which is log n, you get that epsilon j is at most maybe n squared. I mean, if it was a 2, it was a linear, but never mind. And delta j is at most n divided by epsilon m, like that. And you have an epsilon delta that you want, which at this point usually you call epsilon final and delta final just to distinguish them from the rest. But you can see that by taking epsilon prime, let's start here. By taking epsilon prime to be this divided by that, so you take the O smaller, like the hash functions prepare themselves for the iterations. If it was a 4, it was n squared. So, yes. Lazy. So you can take epsilon prime to be like epsilon final over n squared. And then this will affect things here. Because here now, this expression becomes even before delta final. Because of that, this expression becomes, I don't know. I really don't know. It's like, it's m here, not n. It's n. N cubed or to the fourth. Because fifth even. Because it's this square times that. It's fifth. Right? Epsilon final. Epsilon final squared m. And the m is now, and that's exactly the point. Now you look at it and say, it doesn't look good because this is actually smaller than 1, this thing, right? At the end of the day. And you got n to the fifth divided by, it doesn't work for your advantage, epsilon final squared, but then m is coming. Right? Once you have this m here, you can say, well, just going to take m to be such that this will hold. So I'm going to choose m. That's what I said. There is the m, and maybe m is such that this holds already. But if it's not, I'm going to kind of increase m artificially. It doesn't feel right, but artificially. But you can do that. To this thing. And if you remember, the seed length is really log n times log m. Maybe we should call it some other n, but times log m. And now when you plug this, you get what we said. So you get like log n. Right, because, yes. Because when we said what the PRG is, we didn't separate it between the confidence and accuracy. Right. Yes, so you can think of them as, so you can think of them as, right, so now you can, here's the final. You can think of them as just the same if you don't mind. Good. So after the break, I will tell you that this exact PRG with essentially the exact way of analysis is a PRG for read-once branching programs, which is not clear because where are the rectangles? Like, okay, let's have a break and then we'll continue. In the meantime, if you want, I can just say why it's true. Like it's just easy. Unless you want to rest a little bit. Right. So you have like f of x is in A, and let's do even g of x is in B, just because I can. So you're asking what's the probability of this to happen? So that's the same as saying the probability of x is in f inverse A. Right, AH, sorry, yes. No, but yeah, right. In G inverse B. And now you can use the expander mix lemma to say that this is up to some error, approximately.
That's what I'm saying.
No, but that's a rectangle. That's a set.
Oh, yes. Yes.
Right. It's a weird set. It's actually better if it's not one-to-one, because then the sets become smaller. No, larger actually. So that's not better. But anyway, if you want to proceed, because I mean, there's one more step. So this times that. Right, exactly. This is the expander mixing lemma. You need H. You know that for most H's, this works. Right. Unless we probability delta over H, this equality all up to epsilon, up to some error. Right. So you know that the probability that h of x.
So you wrapped into already
the f.
Using the confidence in
Right. So like here, I mean.
No.
Right.
The confidence and the
exactly.
The mixing.
Right. You can do the same. I did separate between the two because I said because there is a separation between the two. So I said acceptable probability that over Hj these two things are that close. Because I want to prove something of that sort, confidence. Right, because I know, what I really know is that this equality up to epsilon prime holds, not always, but this thing holds, right, up to this delta prime, which is 1 over epsilon prime squared. But now you need to f it back. That's fine, right? So this is equivalent to f of x is an a. That wasn't the problem. Okay. But let me just show here. Yeah. Right. Right. So this is only on x, and this is probably up to. This is up to, and this is with respect to h. Yes. And this with respect to epsilon. To x.
So you need so why do you need two?
Two. What do you mean 2 ones? Ah, no, like because it's when you prove this, the Hashem's lemma you use Chebyshev and stuff. You need pairwise. Right? Remember we had this proof where we had the set A and B, and we look at the set S of all elements that in A that goes to B, and we analyze the variance of that. Pairwise. And that's enough, but it's required. Because but if it's one-wise, you know, for example, yeah, I don't know. I mean, and it's a proof.
Oh, you're right. One way is just you can do
X, maybe?
just take the same.
There is no one, yeah. One way just mean, yeah.
And then take one that just jumps one ahead.
Oh, I see.
And it would be wise, but it would be 0.
Right.
It would never be.
Yes, exactly. The seed. Sorry? No, it's from M to M. Yes. Because you want h of x also to be like I mean, this PRG doubles things, but not the hash function.
In the overall analysis, there is still a delta final.
Yes.
But in the PRG, we don't have a delta final.
Right. So what we said is you can incorporate that into the error. So if you have this is a stronger notion. If you have a PRG like that with high probability over some of its randomness, it's accurate over the rest of the randomness. So if you have a PRG, if you have this thing with high probability, say the probability over H of PRG works up to plus minus epsilon. So this is kind of schematic, but if you have a PRG, it has both H and X in it. But with high probability over H, this holds when you go over all X's up to this epsilon, then you can always say that it's kind of anti-Markov. You can always say that forget about the probability over H, just average over all H and X. You'll get error at most delta plus epsilon. Or maybe even like that or something. Yes. Like Markov is the other way around. You can say that if the average is good, then most of the time it's not so bad. And this means I know that most of the time it's good. So it's better. This is like the prototype example of a good low variance. Because usually it's the right thing and sometimes it's not. That's the
So in the overall analysis, we do have to just write epsilon final, right?
Yes. But I'm preparing myself for what's coming next. But in general, it's instructive to separate them because in many settings, confidence costs less than accuracy. That's very like exponentially less. So sometimes it's really beneficiary to throw things like not mix the accuracy and the confidence, like put it in the right place because they are not symmetric. Like in many cases, expanders works, not our expanders, but unbalanced expanders works better with confidence and with accuracy and stuff like that. Yeah, I can't say much about it, but